Okay, 6.4 properties of vectors. So properties used to evaluate numerical expressions and simplify algebraic expressions also apply to vector addition and scalar multiplication. Okay, so vector addition, scalar multiplication. So commutative property of addition. So when we're dealing with vectors, this holds. If we add vectors a plus b, this is also the same thing as adding vectors b plus a. Okay, and we saw this in one of the previous lessons. Okay, the associative property of addition. So this one's a new one. Oh no, this is the same. So this holds as well. If we add a plus b first and then plus c, we're going to get the same resultant as if we add a plus and then b plus c. So this is kind of like adding b plus c first and then adding that to a. Okay, same resultant. Okay, then we have distributive property of addition. So if we have some scalar k, it holds that if k is outside of a bracket of like a plus b, k would be applied to a and k would be applied to b. Okay, that's distributive property. So in other words, we would be adding the scalar k times vector a plus the scalar k times vector b. Okay, as long as k is a real number. This just kind of means that like, oh no, it even holds if it's 0. Just as long as k is a real number. Okay, adding the 0 vector. If you had a vector a and you added a 0 vector, you're going to still come out with vector a. Okay, remember 0 vector has no direction, no magnitude, so you're going to get vector a as itself. Okay, so these are the properties of addition here. Now the last two are the properties of multiplication. Okay, the associative law for scalars. So if we have some scalar m and it's multiplied by some scalar n times vector a, this is saying that, sorry, this is supposed to be an equal sign here. Okay, so some scalar m times some scalar n times vector a is going to be the same thing as if you multiplied the scalars first and then multiplied that by scalar a, or sorry, vector a, or just in order, m times n times vector a. Okay, this can be rewritten however, like with the brackets or without the brackets, however we want to group these, that's fine. All of these are going to yield the same answer. Okay, so in other words, it doesn't matter what order we multiply scalars and vectors in, we're going to yield the same answer. Okay, and now distributive law for scalars. So this is a little bit different than the distributive law, the distributive property for addition. Okay, because we had one scalar and two vectors up here. Now we have two scalars and one vector. So if we have scalar m plus scalar n, and then we had vector a, we would multiply scalar m times vector a and scalar n times vector a. Okay, and we're going to yield the same thing. Okay, so let's take a look at some of these in examples. So I'll leave this up here. Example 1, simplify the following expressions. So we have 3, which is the scalar, times, right, the bracket, 2 times vector a plus vector b plus vector c. And then we're going to subtract vector a plus 3 times vector b plus minus 2 times vector c. Okay, so this, we're going to start with distributive property. So we're going to start by distributing this scalar 3 into the first bracket. So 3 times 2 vector a is going to be 6 times vector a. 3 times vector b is going to be plus 3 times vector b. And 3 times vector c is going to be 3 times vector c. Then we have minus this second. Usually it would be in the form of a polynomial. Now it's in the form of addition and subtraction vectors. So let's go ahead and distribute this -1 into the second bracket. So we're going to have negative vector A, -3 vector B, and -1 times -2 vector C is +2 vector C. Okay, now let's collect kind of like a like term, but like vectors. Okay, 6A minus A, so we're going to be left with 5 vector A, and 3 vector B, -3 vector B, those go away. That turns into a 0 vector, right? If we have 3 vector B's and we subtract 3 vector B's, goes away. Now, 3 vector C plus 2 vector C, we get plus 5 vector C. Okay, example 2. If vector x equals 3 vector I minus 4 vector j plus vector k, and then we have vector y equals 1 vector j minus 5 vector k, and vector z equals -1 vector I minus 1 vector j plus 4 vector k. Determine each of the following in terms of I, j, and k. Okay, so we want to do vector x plus vector y. So vector x is this right here. I'm going to just bracket it. So I'm going to copy this down as though I'm like doing a straight substitution. So 3 vector I minus 4 vector j plus vector k. Okay, and then we're going to go plus, and we're going to substitute in vector y. So vector y has no I component, but it has a vector j minus 5 vector k. And then we just go ahead and simplify. So 3 vector I, that just comes down. That's the only vector I component. And then minus 4 vector j plus vector j, I get minus 3 vector j. And I get plus vector k minus 5 vector k, I get minus 4 vector k. Okay, now, same thing for b except for we're subtracting. So we're going to go vector x minus vector y. So why don't we substitute in vector x, which is 3 vector I minus 4 vector j plus vector k, right? This is vector x. Now we're going to go minus, but we're going to put vector y in brackets because this negative sign is going to apply to that vector y. So let's rewrite this. 3 vector I minus 4 vector j plus vector k minus vector j plus 5 vector k, right? Because when we have a negative sign here, we're just negating all of the signs. So 3 vector I is going to stay the same because we only have one I component. Minus 4 vector j minus j, I get minus 5 vector j. Okay. And then vector k plus 5 vector k, I get plus 6 vector k. Okay, for the last one, vector x. So I'm going to substitute in 3 vector I minus 4 vector j plus vector k. Now we have minus 2 times vector y. So I'm going to put in brackets vector y, which is vector j minus 5 vector k. And then plus 3z. So z is, it's the first time we're seeing this one, negative vector I minus vector j plus 4 vector k. Okay. So in the next line, I'm going to distribute in the -2, and I'm going to distribute in the 3. So I get 3 vector I minus 4 vector j plus vector k, then minus 2 vector j plus 10 vector k, minus 3 vector I, right? 3 times negative 1, and 3 times negative 1 again, so negative 3 vector j, and then plus 12 vector k. So if I have 3 vector I minus 3 vector I, and those are the only I components, those go away to the 0 vector. We don't even have to write it. Okay, so you don't have to write 0 vector I. We just interpret that as the 0 vector. We can leave it out. Minus negative 4 vector j minus 2 vector j, that'll be negative 6 vector j, and then minus 3 vector j, so negative 9 vector j. Then we have vector k plus 10 vector k, which is 11 vector k, plus 12 vector k. So I get, what's 11 plus 12? I get plus 23 vector k. So I get the answer, negative 9 vector j plus 23 vector k.